Thank you. Well, I think this audience doesn't need much reminder of the properties of nuclear star clusters. So I'll be brief. They're compact clusters of stars found at the centers of galaxies. In some cases, the cluster is a really distinct structure that rises up above the bulge or background galaxy in surface brightness. In other cases, like in the case of the Milky Way, it's basically a power law extension of the stellar density outside the central nucleus. That means that the estimates of the mass of nuclear star clusters and the half-light radius are often fairly uncertain, but typically it's somewhere between 3 and 30 parsecs for the radius, and masses between 10 to the 6 and 10 to the 8 solar masses. The stellar number densities are then 10 to the 6 per cubic parsec or even higher. That makes these the densest stellar systems in the universe. And some, but not all, of the nuclear star clusters also contain, of course, black holes with masses between 10 to the 6th and 10 to the 10th solar masses. For the purposes of this talk, when I talk about a nuclear star cluster, I'm just going to mean the system of stars within the sphere of influence of the black hole. And as Kaihan said yesterday, by that I mean the radius where the gravitational forces are dominated by the black hole. That is, the mass of the black hole is larger than the enclosed mass of the stars. I can't resist talking briefly about the relation between nuclear star clusters and globular clusters, which are the second densest stellar systems in the universe. There's a close relation between the two kinds of systems. In particular, we believe that some of the brightest globular clusters are the nuclear star clusters of tidally disrupted galaxies. And there's strong evidence that at least some nuclear star clusters are formed by the in-spiral of globular clusters to the center of the galaxy through dynamical friction. So these two statements are an example of what Niels Bohr called a great truth. His definition of a great truth was that the opposite of a great truth was also a great truth. So the great truth in this case is that globular clusters are formed from nuclear star clusters, and the opposite is that nuclear star clusters are formed from globular clusters. As I've said, the nuclear star clusters are the densest stellar systems. They also have by far the shortest orbital periods of any stellar systems. And that has led theorists for decades to argue that they should be in some sort of thermodynamic equilibrium, but the nature of this equilibrium has been difficult to figure out, and theorists have gone down a number of wrong roads in looking for it. The simplest argument is that the equilibrium should be something like an isothermal atmosphere. So if the gravitational potential due to the black hole is minus gm over r, that would imply that the equilibrium density would be proportional to the potential divided by kT, where k is Boltzmann's constant and T is some sort of equivalent of a temperature. That implies that the density should go like the exponential of 1 over the radius, which of course makes no sense because it implies a divergent density and total mass close to the center. The problem with this particular solution is that it doesn't apply because the stars at small radii are consumed by the black hole through either tidal disruption or direct consumption. And it was Bacall and Wolf in 1976, following work by Peebles, that recognized that the correct solution, at least for a single stellar mass, was a constant flux solution, a constant flux in energy and a constant flux in number, and that those implied a number density going like radius to the -7/4. That prediction of Bacall and Wolf is correct in the sense that it's been confirmed by direct n-body calculations, but its applicability to real nuclear star clusters is not necessarily very good for two reasons. The first is that in many clusters, the relaxation time is comparable to or even longer than the age of the universe. This is a plot of the relaxation time as a function of distance for the nuclear star cluster at the center of the Milky Way. And you can see that the two-body relaxation time is never shorter than a few gigayears, and that smaller radii is longer than the age of the universe. And the reason for that is that despite the very high density and the short dynamical times, the relaxation time due to gravitational encounters goes like the cube of the velocity dispersion. In a Keplerian potential, the velocity dispersion goes like 1 over the square root of the radius. So there's a factor of radius to the 3/2 that largely cancels the growing density. The second problem is that in many clusters, the stellar collision time is actually less than the relaxation time at small radii. Roughly, the relaxation time is longer than the collision time if the velocity dispersion is larger than the escape speed from the stars. So for solar type stars, that's about 600 kilometers a second. And that implies that in inner parts of the nuclear star cluster, two-body relaxation is not an important effect compared to direct collisions. We now recognize, however, that there's an alternative relaxation mechanism that's faster than standard two-body relaxation, because we're in a regime where the black hole dominates the gravitational potential of the nuclear star cluster. On timescales much longer than the orbital period, you can treat the orbits by taking a time-lapse exposure of them, so their mass distribution looks like a wire or a Keplerian ellipse, and each wire exerts torques on the other wires that lead to relaxation of the angular momentum of the orbits, but not the energy. In a Keplerian potential, the energy depends only on the semi-major axis. So a simpler way to say that is that in resonant relaxation, the semi-major axes are fixed. Given subject to the constraint that the semi-major axes are fixed, relaxation will try to maximize the entropy of the stars at each semi-major axis. It does so much faster than relaxation due to two-body encounters, and that implies that over a wide range of radii, you might expect that the cluster should be in a maximum entropy state. And the difference from standard relaxation is that the constraints are not just the total energy and total angular momentum, but also the semi-major axis distribution. And if you do simple models for, again, for the galactic nuclear star cluster, you can see that the resonant relaxation time is as short as 10 to the 7th years, and over a wide range of radii is at least an order of magnitude faster than the two-body relaxation time. So how does this, what does the maximum entropy state look like? I'm going to look first at the simple case of a toy model in which all the stars have the same mass, they all have the same semi-major axis. Ignore the effects of general relativity, ignore the two-body relaxation, and ignore the consumption of stars by the central black hole. This is such a simple system that it's characterized by only one parameter, which is the initial energy. In this sense, the initial energy is the self-gravitational energy due to the stars. A low energy example would be a system in which the stars are initially spherically distributed on nearly circular orbits. A high energy example would be where the stars are in nearly radial orbits. And then you just calculate for this simple toy model what the maximum entropy state looks like as a function of energy. There are many properties of the state that you can look at, but the one I'm going to focus is on the question of whether the maximum entropy state is spherical. And the simplest way to measure that is to use the eccentricity vectors of the orbits. These are vectors that point towards the pericenter of the orbit, whose magnitude is equal to the eccentricity. So for a spherically symmetric system, the mean eccentricity vector ought to be 0. And if the orbits were all highly eccentric and aligned, the mean eccentricity would be unity. This is a plot of what the mean eccentricity looks like as a function of energy for this toy systems. For systems with relatively high energy, that is biased towards radial orbits, the eccentricity vector is 0 and the system is spherical. But at a critical energy, you see a discrete phase transition towards a lopsided state. And as the energy becomes lower and lower relative to this transition energy, the eccentricity vector gets bigger and bigger, and the cluster becomes more and more lopsided. This is based on semi-analytic calculations of the maximum entropy state. It says that there's an order-disorder phase transition, which is exactly analogous to the Curie point, marking the distinction between unmagnetized and ferromagnetic materials. This calculation can be verified in a host of different numerical techniques. This is a simulation of the same system using Markov chain Monte Carlo. The phase transition is at a slightly different point because in Markov chain Monte Carlo, you have to soften the gravitational potentials a little. What the system characteristically looks like at an energy around here is shown by this graphic. The black hole is here. The eccentricity vectors are aimed in this direction. And the strong enhancement in the density is because stars travel slower at aphelion when they're furthest away from the black hole. So they linger at this point and create a much higher density here than at other points in the star cluster. So far, various experiments by various groups have found the lopsided transition, both in analytic models, as I said, in the Markov chain Monte Carlo, in models of a scale-free cluster, which is sort of the opposite of a cluster where everything's got a single semi-major axis. In simulations using n wires, that is an n-body simulation, but using the averaged orbits rather than point masses. It's been seen in simulations of a cluster following the Bacall-Wolf law. It's been seen in numerical simulations looking at maximum entropy states of a cluster. The only technique that I would like to see it still verified in is direct n-body simulations. These are extremely hard for nuclear star clusters, and they simply haven't been done for the right parameters to find the transition. The obvious observational application of this is to the nuclear star cluster in M31. The Hubble telescope, following early work by the Stratoscope balloon telescope, found that the nucleus was double. There's a bright, diffuse reddish component, plus a fainter, bluer, more concentrated component. At the center of the bluer component is a black hole with a mass between 1 and 2 times 10 to the 8th solar masses. The bright component is a thick disk of stars orbiting the central black hole with a typical size of a few parsecs. The small blue patch of stars near the black hole is a set of a few hundred recently formed A stars. Models of an eccentric disk like this match the photometry, reproduce the rotation and dispersion curves, and they even predict the offset of the black hole because it's the center of mass of the eccentric disk and the black hole that should be at the bottom of the potential well of the larger galaxy rather than just the black hole. The reason this is relevant, of course, is that it says that one of the 2 giant spirals in the local group contains a lopsided nucleus. Most larger distances, we wouldn't have a chance to resolve a lopsidedness in a nuclear star cluster, even with Hubble. But if 1 out of 2 in the local group is lopsided, it suggests that the phenomenon is fairly common. And that's just a reminder of the simulation of the concentration of stars at apocenter, which is almost certainly exactly what you're seeing in the case of M31. Okay, let me summarize. It seems clear from the dynamics that nuclear star clusters can be subject to an order-disorder phase transition. And then in the disordered transition, they change from a spherical equilibrium to a lopsided equilibrium. The transition has been verified in models with a wide variety of properties and with a wide variety of different numerical techniques. Of course, what we don't know is the eccentricity distribution of stars in the nucleus, and therefore we don't know whether the nuclei that we observe are susceptible to this transition. The transition requires that the initial state is cool in the sense that the RMS eccentricities are less than about 0.3. The most natural way to cause that cooling is through processes that either remove stars on radial orbits or add stars on circular ones. So for example, consumption of stars by the central black hole, since most of the stars that are lost are on nearly radial orbits. Formation of new stars in disks, which would be in circular orbits, and which we see in the galactic center star cluster and in M31. And finally, if the clusters are formed by in-spiral globular clusters, those would likely in-spiral on nearly circular orbits and add stars on nearly circular orbits. The relevance of the lopsided star clusters to the question of this session, the rate of black hole growth in the local universe, is that the lopsided state is likely to have a much higher rate of tidal disruption. In spherical systems, the disruption occurs through two-body relaxation, but in a lopsided system, there are large-scale gravitational torques that change the orbital angular momenta of the stars much more efficiently. Similarly, you'd see much higher rates of consumption of stars and of extreme mass ratio in-spirals. The quantitative estimates aren't available yet, but I think that's one of the things that we want to try to understand. So we don't know how common lopsided nuclear star clusters are, but half of the giant spirals in the local group are lopsided, and so it's likely that it's a fairly common phenomenon. Okay, I'll stop there.
Super.